Hello everyone and welcome to a new discussion which is part 4 of DM's derivatives. This is the last part in the derivatives, but we will keep discussing about the applications of DMs and also few more derivatives. But we have categorized them, so this is in that sense it is part 4 and derivative. As you know that DM is a raster representation and which represents a continuous surface. So, that is why it is also continuous data, contrary to like contour or point data which is discontinuous or discrete. So, here we are having continuous data and currently not only we use or reference to the surface of the earth, but digital elevation models of Mars and Moon surface are also available, because there are many satellites which are orbiting around these bodies like the Moon or a planet like Mars, and they too have created digital elevation models for these surfaces as well. So, this is not only the surface of the earth, but DMs are now available for other surfaces also. Now, these as you know that they are modeled, because that is why in the name itself the digital elevation model. So, this is not the reality, and the real world is at 1:1 scale. So, this is scaled down, therefore, we say a model or an abstract form of reality. So, here the surfaces, these terrain surfaces, undulations, whatever present on the surface of the earth, they are all modeled one, they are not the real one. Because why modeled? Because each cell is representing a single elevation value, and if it is a say 30 meter resolution, that means for 900 square meter we are having just one elevation value. But if terrain is highly rugged like Himalaya, then within 900 square kilometer you can have varied digital or elevation values. But they all have been averaged down and a single value, elevation value has been assigned against that cell. So, that is why it comes under the category of model, because it is not the real world, it is the abstract form of reality which is representing the terrain surface. Now, also we know that in various analysis, instead of surface, sometimes we instead of using continuous data, still some people prefer using discrete data. Even for ourselves, sometimes we have to go back from continuous to discrete. That means why I have used word go back, because I understand that the continuous data is a hierarchy. In hierarchy it is on the top, like a tin model also. But point data or line data or polyline or contours data are the discrete data. So, they are in that sense, they are not in hierarchy in the top, they are in the bottom like point. But sometimes for different applications we have to convert or create contours using a surface. So, that we will be discussing for what purposes we are and how to do it on a GIS software. So, as you know, either DMs or TINs are created, though they are created either from point height data sets or contours. But sometimes we have to reverse the process, and still many people are very good of understanding contours rather than DM. So, because the senior people, those who started initially with contours and studying the contours in topographic maps, they are still find very convenient to use contours rather than DMs. Working with my senior colleagues several times, I have found that whenever I have showed digital elevation models to them, they were very uncomfortable, and they said, can you produce this thing in form of contours, so then I will understand. So, for such people also, because sometimes they are the decision makers, the senior people are decision makers, and their understanding has to be very good about the terrain, otherwise the decisions might be wrong. So, whatever they are asking, we should be able to produce the products according to their choices or preferences. Like here, what I am depicting here is in the corner what you are seeing a digital elevation model, which you can see that this digital elevation model is here, and then in the bottom left you are seeing a hillside, that is the shade relief model derived from the same digital elevation model. These two images or these two data sets you must have been seeing in various presentations or lectures of this course. So, this is that same data set. What on the right side of the bigger one, what it is showing is the hillsides with the contours. So, what I have done, I kept the hillside in the background and drive the contours. And because I am having a continuous surface, that is my digital elevation model. So, declaring to the system that I want contour intervals starting from here and with this interval. So, whatever the interval I decide, whether 1 meter, 10 meter or 20 meter, because remember one important thing here is that though spacer resolution might be 30 meter, that is the in horizontal scale, but vertical scale, that is the Z unit, is in meters. So, maximum I can drive contours of 1 meter interval, that is the the best possible. If suppose this digital elevation model might have been prepared using contours of say 20 meter intervals, but after creating a digital elevation model, now I can create contours even at 1 meter, because the least count in my vertical scale or for Z or for elevation is 1 meter. So, that is another advantage of how to get more, because for small area even 1 meter contour will matter a lot, but for a highly rugged terrain 100 meter contours may create cluttering in your map. So, depending on the unevenness or ruggedness of the terrain, sometimes we change the density of contours. How you would do it in a standard GIS software, for example in ArcGIS, but I am sure all these softwares support some. I am having experience of like ArcView, ILVIS or other softwares, they all supports what you have to provide: elevation grid, that is the input raster, you have to provide where it will be stored, and then contour interval. So, here in this example I have taken contour interval of 200 meter, you can take even 1 meter, and then base contour I said okay, start with 0, does not matter, and then of course the Z factor. In many such options Z factor will be keep coming. So, that accordingly depending on your data set, because the example which I have taken is all in meters. So, I can keep Z factor 1, and once you say okay, you can drive contours as you have seen in this right picture. Now, another advantage is sometimes I am interested only in one particular contour or one particular I want to drive, rest I do not want, because I might be looking for my route alignments, for road alignment or especially for rail track alignments, I might be looking a single height contour, or for my power channel, for canal network in hilly terrain, I might be looking a route which is having the same elevation. That means nothing but is a single contour. So, single contour can also be derived, that instead of interval I would use some and not give the interval. Interactively also the tools are available in the software, that wherever I will put my cursor and click, I get that contour, or you can just put the value that I am looking the contour which is having this height or this elevation or this value, and accordingly it will be drawn. Because in real projects many times you are looking various things, you want to drive various things from one single digital elevation mode. So, all this is possible, though as I have said this is a backward kind of process. From a continuous data I am going for discrete data, but for certain projects these are very helpful things. So, such information like single contours becomes useful when on spot decisions are being made, because nowadays it is possible to carry even a small version of GIS on a laptop or a full version, and where the decisions are being taken on the field, I can drive the products immediately there also. Now, this was the from continuous to polyline. Now, continuous to points also, that is the lowest in the hierarchy, and that is sometimes also very much required for various kinds of comparison, various kinds of clustering studies, and comparing with some point distribution with other point distribution and so on. Some example I will just show you from my own domain, that the first points are generated. So, random points are generated for that extent for which I am having a digital elevation model, and then later elevation, that is the Z value, would be added, or in some software language like in ArcGIS it is called 3D point. 3D point means that attribute is having Z value. So, then it becomes a 3D point. For example, here what we are seeing, that input this is output location, random points are there, and I have declared that how many random points I want, what should be the extent of the data, and once I say OK, I get. So, this random time tools are available in data management. This I tell you, this random point tools, random point generators are very useful. You can have the creation of random points, you can select the random points, and they are very useful in various kinds of analysis which involves the point data. So, this is very important from that point of view. So, likewise I have created now random points, and then we collect the Z value from the digital elevation model which is shown in the background. Then my point becomes a 3D point basically. So, like here 100 random points are generated within the extent, the DEM extent. Extent you have to always give. So, you if you want to perform on say this digital elevation model, then extent would be given, or you can change also extent, this extent or the area of interest, but generally what from which digital elevation model I want to pick my Z values, the same extent one should select. Now, what are the other applications of random points? That points pattern analysis. This is very important for many kind of analysis. Like I want to compare the earthquake epicenters and when want to see how if these number of earthquake epicenters are distributed randomly, whether there is some pattern or not, or any kind of data collection or any kind of checking, also these random points becomes very useful. So, based on this analysis is always very useful for various applications. So, this point pattern analysis basically is the evaluation of the pattern or distribution of a set of points on a surface. Now, these points which we have collected here, for example 100 points, they are statistically tools are used to correlate with other point distribution within the same extent, where the sum values related to the sample even points are compared to the random points. So, if I, as I gave the example, if I am having the distribution of epicenter, earthquake epicenter locations, then I can try, if I am having say 100 epicenters, I can create random 100 points and then can compare based on statistical analysis, and basically this statistical analysis involves the distance among the points. So, if the distance among points is less, that means they are having some pattern. But if they are randomly distributed, then the distance is going to be quite large. So, for example, I have already given this example that earthquake epicenter distribution, these might have some pattern while comparing the random distribution. While I expect pattern, because generally they are located along a fault line, a geological fault line or a structure. So, that is why this can be compared with the random distribution very easily. Now, another set of issue which can be solved by using this point pattern analysis, which is the concern the relative pattern or arrangement of patterns. For example, here same number of points are taken in all these three examples in this schematic. The first one is the random points. So, how randomly these are distributed, whereas this is the uniform, that means in the each box there are 2 points and there is a pattern, there is everything is fixed. So, that is why it is uniformed, or you can say organized distribution. However, this is clustered distribution, that means only in 2 blocks here we are having all these points which are either randomly distributed or uniformly distributed. So, this like clustered, there can be a linear arrangement or distribution also. So, immediately then things can be compared using the distances among all those points. So, point patterns can be categorized as the random, uniform, clustered or dispersed along the 2 continuous or 2 continuums. Now, the random versus uniform, that is stratified or regular, we can decide that. And so any distribution of points can be assessed comparing with the random distribution, clustered or dispersed, that too we can do this kind of. So, two continuums can be done, whether the points are uniformly distributed or randomly distributed, whether points are dispersed or clustered. So, all these kinds of analysis can be done. Like for example, I am taking here this is the as you can see that add Z information. So, I am creating a 3D points against the distribution of these random points which I have generated in number 100, and then their Z values are added, as you can see here that the Z values are added here. Generally when you create because attribute table of point data will be populated with the Z value collected from the digital elevation model which is in the background. So, that creates all our points as 3D points. 3D again I have said that means they are carrying Z value also. It is not necessary that all points will always carry Z values, but if you are having points and same time you are having corresponding digital elevation models, for some applications you require Z points, you can definitely collect using such tools available in standard GIS softwares. Now, another related thing is while handling digital elevation models, that sometimes these you have to create mosaic of DMs. Now, question is why mosaic we should create? Mosaic is created because lot of free DMs which are available through net, they are available in tile forms. Generally you will get 1 degree tile or 5 degree tile. 1 degree tile means 1 degree latitude and 1 degree longitude, that much area, roughly 110 by 110 kilometer area will be represented by one tile if it is 1 degree. Now, your area of interest is covering will cover in 4 tiles. So, individual tiles are available, you have to download and create a mosaic of these tiles. But interestingly, some sites are there which are using your area of interest as polygon or extent which you give in terms of latitude longitude, and that site will create a mosaic of these individual tiles and will give you a big mosaiced DMs. But the problem is that because it is easy to download individual tiles, but if there are 10 tiles are involved, the size of the file will become very large, and therefore sometimes it may be difficult to download from net. So, it is good to download these tiles, because this is how the data is kept nowadays in form of tiles for global scale data, and then you can mosaic these tiles. So, how they are mosaics? Basically that the mosaicing merges basically adjacent tiles, multiple existing DMs tiles into an existing DM or raster data set. If you are having a raster data set, fine. If you do not have, no problem, 4 tiles can be merged and one single file can be created. So, it is required because, as I have already mentioned, that many global DMs are available in tile forms. For example, here what we are seeing 4 tiles. So, employing this mosaicing tool, I can create a single tile without any seam, because first this digital elevation model, global scale digital elevation model was developed, and then tiles were created, and therefore when we create again a mosaic, there should not be any seam, otherwise it will become less reliable or useful data. So, a seamless mosaic of digital elevation models can be created even if they are available in tile forms, and generally all these downloadable digital elevation models available from various resources or sources, internet sources, all are available in tile forms. No problem, it is not a problem at all, it just requires a few more minutes to create a mosaic and then can you use it. Now, so our area of interest must be known to us, and then only you get the appropriate tiles and then you can mosaic. So, our area of interest may not fall within one tile, or therefore mosaicing is required to merge few adjacent tiles. This is a very common step and common problem also, because you may find if it is very small area, you may find that it is falling in just one tile, but if it is a little large area, you may find that it is falling in minimum 4 tiles or 8 tiles or 20 tiles, doesn't, it depends on the area of interest, the size of area of interest. So, mosaic is useful when 2 or more adjacent DMs needed to be merged into one entity. And some mosaic techniques can help minimize the abrupt changes, that means seamless. So, in case of satellite images, creating a seamless mosaic is very challenging, because 2 adjacent satellite images may not be representing the same date data of the same year, and therefore, because the atmospheric conditions might change for day 1 to day 2 of these 2 adjacent tiles of a satellite image, then seamless mosaic becomes very difficult. And that is why you see on Google Earth, many times if you zoom it and you encounter a boundary or a seam, that is the reason, because 2 adjacent scenes are having different ages or different dates of acquisition. And this is also there because each satellite is having its swath width, that is the fixed. Like for example, NOAA AVHRR, which is having roughly swath width of 2800 kilometer. So, one strip of 2800 kilometer is being scanned every time whenever the satellite is orbiting around the Earth. Whereas, if I give an example of IKONOS, which covers only 11 kilometer of the strip of the Earth, and therefore, if my area of interest is very large, that means I have to get lot of these adjacent coverages or adjacent scenes of IKONOS to create a mosaic. And when I will do it, I will have problems, because these strips or scenes may be representing different dates. It is highly likely that they will be representing different dates. And meantime, the atmospheric conditions might change, and it becomes very difficult to create a completely seamless mosaic of satellite images. But it is rather very easy to create seamless mosaic of digital elevation models. Now, these overlapping areas of mosaics can be handled in several ways. This is mainly true in case of satellite images, that one can set the tool to keep only the first raster data sets or can blend the overlapping cells. So, if in case of satellite images it happens that there are overlapping, so you can choose while creating these mosaics. And there are also several options to determine how to handle a color map, because these satellite images you might be handling as false color composite. So, there also the colors can also be managed, that you can say that whichever on the top, all the scenes should follow that color scheme or that color map. So, accordingly things will be done, but still in spite of all these options, still it is very hard many times to create a completely seamless mosaic of satellite images. So, there are different advanced techniques are also there, but still it is no technique is yet perfect to create a completely seamless mosaic of all satellite images, because of different dates they have been collected. Now, another exercise which we keep doing in our handling of digital elevation model, that is creating a subset or a clip or extract of a DM. So, this like for satellite images also, even for point data, even for line data, we have to create a subset. So, there are tools creating subset of raster, creating subset of vector. So, what is basically the requirement is that you should have your area of interest in form of a polygon. Therefore, clip or extract a portion of a digital elevation model or a satellite image or a point data or a polyline data or even a polygon data, you need a polygon. That polygon can be a district boundary, can be a country boundary, can be a state boundary, or can be a hydrological boundary like a watershed, basin or catchment. So, this polygon has to be there. Based on that, we can extract or clip or can create a subset of a digital elevation model. So, this clip output includes any cell that interact or intersect with the overlapping polygons. For example, here I am in most of the examples I am using the same digital elevation model throughout which I started in the beginning. So that you become, every time if I change digital elevation model, things becomes unusual. So I am keeping constant, almost constant the digital elevation. Now here what you are finding that the red one is the watershed or a hydrological boundary which I am taking. My target is to clip or create a subset representing the digital elevation model only for this watershed. So it is not a problem. What I need a DM and a polygon boundary, and of course I am having drainage network and other thing that I can clip separately also, and this is what I have done. So DM and drainage network has been clipped using watershed boundary. So two examples, one is clipping a raster, that is our digital elevation model, and clipping or creating a subset of drainage network that you are also. So polyline, point data, polygon data or raster, whether image or a DM or a grid, for any such data this subset can always be created except one, that is subset of a tin. Subset of a tin can never be created. So remember this thing, that is the limitation there. Now the DMs and derivatives which we have been discussing, what we have completed so far is the first order digital elevation models or primary derivatives also. Some people would like to classify like primary, secondary, tertiary, but I say if I say first order derivatives, then among them is the slope, very common one, then I am having the aspect, and then hillside. These are, we can put them as first category. Contours also, that is discretization, say first order derivatives, we can point heights, creating a 3D point kind of thing. Now among this second order derivatives, we have already discussed few of them, like curvature of the slopes, different types of curvature, total curvature, standard curvature, convex, concave, all these curvatures we have discussed. Then we have also convergent and divergent flow. These are useful, such analysis are useful from erosional or depositional point of view. And then third order derivatives, under this category comes the drainage network, and that we will be discussing in future. Also the watershed boundary, and this all will come through the surface hydrologic modeling. This part we have already discussed, the topographic position index and also topographic wetness index, which will come through this surface hydrologic modeling. And then sediment transport index, this is also a product through which it can be created through surface hydrologic modeling. Viewshed is a different kind of analysis for which surface hydrologic modeling analysis does not require. It is a different thing, though we have already discussed this viewshed. So these two we have already discussed, other four will be discussed in surface hydrologic modeling. Now when I compare, I have done some comparison of first order derivatives using tin and DM. And what are the variations which we will be seeing? This is very interesting. So what I find that when I drive first order derivatives, then the boundary issues will come always with the tin. So that one thing very important. Now this is first order derivative about the slope. So for the same terrain, two different outputs, because here I am having a raster in form of digital elevation model, and here on the right side I am having tin. So because tin is represented through triangles, facets, and therefore in your slope map it is looking like this. Now in nature things may not be exactly like tin or DM based slopes, but because these are all models. So it is not necessary that everything will match in the ground, but what it should match is the inclination or slope values, that should match against the certain point locations in the field. Whether it is a tin or raster based slope map, these should match. But when we see in a more larger perspective, means for whole area, then the representation of slope maps through two different data sets, through two different data representation models can be completely different. Now boundary issue will remain always with the, now same with the aspect, like slope the derivatives are different, but overall representation is almost same in raster except that units are in tin are triangles. So therefore, that influence is always there. These triangles can be made smaller if we are having large density or a huge density of our observation points, which will be used to create a tin. Then you may create tin of smaller triangles, and also one more condition is whether the undulations are there or not. That means these point inputs are having variation in z value or not. I may have a high density of points for creating a tin, but if those points are not having high variations in the z value, then again larger triangles would be formed. So nonetheless, we can definitely see the differences in the outputs of a raster based aspect and a tin based aspect. Boundary issue will always be there. Similarly, a shaded relief model or a hillside which you are seeing, these are the few derivatives which can be derived from tin. So, I am comparing with the DEM also, but the DEM can drive or can create many other products which tin cannot do it. Anyways, but the best part is that for certain certain derivatives which you are happy with tin, you can still use, and whenever you feel that now you want to have a raster, you can also convert tin to raster. That is also possible, because remember the input is the point data. So, using those point data, again a surface can be created through interpolation techniques. Now, if I do it with the same contour interval, if I do it for contour and derived from a digital elevation model and contours derived from a tin, again the representation is going to be the different, but overall it is almost same, because values are not going to change. Of course, the boundary issue will always be there. In case of raster, the overall shape, as you know, can be either square or rectangular, but in case of tin it is arbitrary. It is not necessarily always square or rectangular. Rarely it would be a square or rectangular. Now, sometimes when we do, this is a little different topic related with, of course, digital elevation models, and when we are going for interpolation, creating a surface, because it is not necessary that all the time whenever we are doing interpolations, we are only doing for a typical elevation model. We may be using point data for creating a surface for groundwater, for pH value or EH value or some other element, any or pollution or other things. So, whenever this situation comes and my area of interest is, say in this example, is shown as a bracket or a rectangular, what I need to do always to take points which are going even beyond my area of interest. The advantage would be that if I take only points which are falling within my area of interest, then in the border areas the interpolation techniques will do extrapolation, and extrapolation can produce lot of errors. But in this case, like I am having the extent of my point distribution is larger than my area of interest. So, what would happen if I use these points and data for creating a surface using interpolation techniques, though there will be extrapolation in the area outside, but at least inside of my area of interest there will not be any extrapolation. And once a larger digital elevation model or a simple surface has been created using these extended points, what I need to do, I will just use this same polygon or this rectangle and create a subset of that digital elevation model. So, that digital elevation model will not have any cell value which has been created through extrapolation. All the cell values would be through interpolations, and this becomes very useful because the error part would be very less. But if I take only for my extent, like for this rectangle, then at many places like here there will be completely extrapolation. So, these areas will have errors because I do not have any observation beyond this boundary. So, it is always better, if that is possible, choice is there, do it. So, the first step, how to handle boundary issues. The first step, the boundary issues problem to consider more data than area of interest or more points. While doing such operations, interpolation, slope aspect, etc. derivatives. So, boundary issues will not come in this. Now, similarly, the second step here, as I have also mentioned, that after interpolation, slope aspect, etc., use AOI polygon, like here this one is shown as a rectangle, red rectangle boundary, and extract tool or clip tool, and through which you can always create. Like here, how to handle boundary issues, which we have done it. One important point which I want to bring here is recall the discussion related with no data. So, this must be, this water set must be having a rectangular area like this, but here it is being represented in the outside of my water set, it is being represented through no data, and no data has been assigned by default, or you can assign a background value of my screen. Generally it is white. So, then I will not see any no data, I will see digital elevation model or my drainage network only for my area of interest. So, this is how your these things work very well. Now, a little bit more about the hypsometric analysis, which is again a DM derivative, and lot of research is being done using these things to understand the terrain, topography and fluvial processes as well. So, what we basically try, hypsometric plots. Hypsometric plots we drive, and if like in this schematic, if I see that my curves are coming like this, then I say that it is a very young topography. But if these plots are coming like this in the bottom, like, then I say the oldest. So, how old that surface is, that can be assessed through hypsometric analysis. Now, these are very useful where lot of tectonic activities or erosional activities are taking place, because of these activities our valleys or surface or slopes cannot become older, they keep changing, and therefore, if we do the hypsometric analysis, which is basically relative area versus relative altitude, we may get curves like this, these thick line black line curves. So, these will represent very younger terrain. So, any terrain using the age factor, or we can indirectly use from tectonics point of view or erosional point of view. So, hypsometric curves is a histogram basically, or cumulative distribution function of elevations in a geographic area. So, this is basically relative area versus relative height, and a hypsometric curve is one which is plotted to indicate the proportions of the area earth surface at a various elevations or depths above or below the certain datum. So, here we will be discussing only above the datum. For example, this is a schematic. In this one what we see, that in mountainous terrain like Himalaya, we generally would see a hypsometric curve like this, but when it goes in the plain areas, in the continental part, we may see like this, then in ocean shelf area something like this, and then deep ocean floor area we would see like this. So, in continental shelf this is the scenario, and in ocean area this is the scenario, and it is a trench, if it is a trench area like very famous Mariana Trench, you may find the profile like this. So, how it has been plotted, that the percent of the earth's surface versus the elevation. So, obviously in the we say that Himalaya is a young mountain chain, therefore, our in this kind of plot we will come here, and these curves will be like this. So, the best known example is for entire earth's surface, which is shown here, that the most significant fact emerging from the curve was discovery that the earth's surface is divided into two statistical distinct levels or steps. The continental platform, that is the land part, about 100 meters above sea level, and the deep sea floor, that is 4700 meters below sea level. So, we know that exactly mountains and continental plains are one and then rest are in different. And if Earth's crust consisted of randomly distributed materials, one would expect a simple Gaussian curve with a peak of about 2450 meters, so that the discovery of two levels suggested that there was continental crust and oceanic crust. So, a lot of interpretations, if we go for a global scale, can be done, and also if we do this analysis for a local scale, like here in this example has been done for Kutch region of Gujarat, which is tectonically very active region, hypsometric analysis for different drainage basins. It is always good to perform such analysis based on hydrological boundaries, because this is how the water flows and erosion and other things will take place. And these are the various water sets which have been considered in this analysis. So, we find that because in this region, though there are tectonic activities, but still these hypsometric curves are not taking this kind of shape as will happen in case of Himalaya, but they are little taking near older kind of topography. And one more example here you are seeing, and one more example for different water sets which you are seeing here, and likewise. So, one single digital elevation model and tens of derivatives, more than 20 derivatives so far we have discussed, and few more will be coming. So, that is why I have been saying repeatedly before I end this discussion that digital elevation models and satellite images are a storehouse of information. It is your capability, how much you can exploit these surfaces or these raster data sets. With this, I thank you very much.